Alright, so in the last class we went through what was known as the electric potential at a certain place. Okay, how do you define electric potential? Quickly, how do you define electric potential? What is electric potential right here at this spot?
The differences in voltages on the side.
You know, electric potential. I'm not talking about difference, potential difference. Potential. Yeah.
The amount of work to take one unit of positive charge from infinity to a point in the field.
Exactly. So at this point, how much is the potential goes by this definition. How much energy do you need to put in, or how much work do you have to do in order to transport one positive 1 coulomb from infinity to that spot? That's called electric potential by definition. Now, what is electric potential difference? It is the amount of energy required to take 1 coulomb from one spot to another spot. It's comparing two spots. So over here, there's an electric potential. Over here, there is another electric potential perhaps. So what is the potential difference? It is the amount of work required to take it from here to here only. Okay? So that's potential difference. And we saw that in an electric field. An electric field runs always from a high potential to low potential. Okay? So if you have a charge Q sitting here, a positive charge, let's say, you know the electric field is running outwards, right? So the electric field is running outward from a positive charge. And how much is the electric potential at different points? The electric potential here is going to be KQ over, let's call it R1. That's the electric potential there. Now what is the electric potential here at this point? It's going to be KQ over R2, right? Because it's far away. So the electric potential equation is KQ over R1. We saw this equation, right? There's no square. If you have a square, that's for what? If you have KQ over R square, what is that for? That's the electric field. So if it's just KQ over R, it is electric potential, which is a scalar quantity. So this is KQ over R1, which is R1 from here to here. And KQ over R2 is the total distance from here to here. KQ over R2 is the potential at this point. Which is bigger? Which is a bigger potential? This one, right? Because this R1 is a smaller value, so automatically this one is a bigger potential. So this is a bigger potential, and this is a smaller potential. So this is a higher potential, and that's a lower potential. Look which way the electric field is running. Electric field always runs from high potential to low potential. Always electric fields run from high potential to low potential. Any field for that matter runs like that. See, gravitational potential is higher here and lower here. And which way is the gravitational field line? Right? Gravitational field lines are going from higher potential to a lower potential. The same way as the electric potentials goes from higher potential to lower potential. So there is always electric field from a higher potential to lower potential. So if I release a unit positive charge, or if I release a positive charge over here, it's going to run from high potential to low potential. If I release an electron here, it's going to run this way. An electron goes in the opposite direction. It goes against the current. Yeah, against the field. Yes?
Potential is a scalar force, right? Or a scalar.
Yes. Potential is a scalar quantity, whereas electric field is a vector quantity. So potential is a scalar quantity. So you don't have to worry about the directional part of it. So how much energy is needed to take something from here to here does not matter which way you're taking it. I can take it like that, or I can just take it straight down here. It doesn't matter. Work done is exactly the same, because you just go by the energy difference. So electric potential difference is the amount of energy required to transport 1 coulomb from one spot to the other spot. So that is what we call as potential difference. Yeah.
So if it's, say it's a negative charge in the middle right there, so is the R1 still a higher potential or no?
Then it will be negative value.
Okay.
Value will be negative. So suppose you have a negative charge then the fields are going to be directed like this. Now, what is the potential value here? The potential value here is KQ over R1. Now, remember, this Q is a negative value. So the whole value is going to be a negative 1. So, and here is going to be KQ over R2. And that's going to be a negative value. So this is going to be a smaller negative value, right? So it's going to be like negative 100. No, negative, let's say 50. And this is negative 100. So which is a bigger potential? Which is a bigger potential, negative 100 or negative 50? Which is a bigger potential? Which is bigger potential? Negative 100 or negative 50? Negative 50. So, yeah, so that's the reason why the electric field is directed from the negative 50 to the negative 100. You understand that? Good. Any other questions right here? So, if the potential difference is, say, delta V, potential difference, what does that mean? It's the amount of energy needed to transport 1 coulomb across. That's what potential difference is. So if I have 2 points, and if the potential difference from here to here is delta V, that simply means you need to do that much work to transport 1 coulomb. Suppose you are transporting Q coulombs across, how much work will be required? If it is 1 coulomb, you need delta V. If it is Q coulombs, and that will be the amount of energy required. So the energy or work done to transport is equal to Q delta V. So if you want to transport Q coulombs across, right now, the work is Q delta V. This is the amount of energy needed to transport Q coulombs through a potential difference of V volts. And of course, the unit is going to be in joules. So if you're transporting Q coulombs through a potential difference of V volts, it's going to be. So from here you can see potential difference or potential definition of, so potential difference is work done per coulomb. So it is joule per coulomb. I think we saw that. We saw that last time, right? Joule per coulomb thing. So the potential difference is joule per coulomb. That's the unit of potential difference. Now when you talk about very small amounts of energy, when you talk about very small amounts of energy, when you talk about very small amounts of energy, you can't always write in terms of joules. Okay, so we define an electron volt. So electron volt as a unit of energy. We'll be using it in multiple places later. In atomic physics, we'll be using electron volts. Even here, we will use so what is the electron volt? Electron volt is not the unit of potential. It's not a potential difference kind of thing. It is the unit of energy. How small is that energy, and how is it defined as? What is 1 electron volt defined as? You can write that definition down. 1 electron volt is defined. 1 electron volt is defined as the energy acquired by an electron. 1 electron volt is defined as the energy acquired by an electron when accelerated by a potential difference of 1 volt. 1 electron volt is defined as the amount of energy acquired by an electron when accelerated by a potential difference of 1 volt. You get it? So if I have a potential difference between 2 points, so between these 2 points there is a potential difference of 1 volt. And if I want to transport 1 electron from the higher potential to the lower potential, I need to do work. Okay? So if I taken the electron right there, which is the lower potential, and if I release it, what will happen to that electron? It will rush to the other side, right? How much energy is it going to acquire as it rushes past? This much, 1 electron volt. So the formula for work done is Q delta V, right? So we know this equation, and that's exactly the same equation. So how much is the work done on 1 electron? So the work done is equal to 1 electron charge times 1 volt. 1 electron charge, Q is E, and what is V? V is 1 volt. By the definition of electron volt, it's amount of energy acquired by an electron when accelerated through a potential difference of 1 volt. So this basically is 1.6 times 10 power negative 19 coulombs times 1. So the answer is 1.6 times 10 power negative 19 joules. And that's what we define as 1 electron volt. So 1 electron volt is equal to 1.6 times 10 power negative 19 joules. That's a conversion factor. And this is actually given in the formula sheet, in the data sheet. But still you need to know what it is and why is it that number. So 1 electron volt is such a small unit. So sometimes you'll see in a problem they'll say calculate the energy in electron volts. Okay? Not in joules. They'll ask you to calculate in electron volts. So what do? You get the amount of energy in joules and then divide it by that number. If you divide it by that number, you're getting the answer in electron volts. Okay? So when you divide it by this number, whatever energy it is, you'll get the answer in electron volts. So electron volt is a unit of energy and not potential or potential difference. Now, equipotentials. Equipotentials. There's a thing called, what is that? Equipotential. What does it mean? Equi means the same potentials. So equipotentials are points or lines where the potential is exactly the same. So if I have a charge sitting here, at this point the potential is kq over r, correct? Where else will it be kq over r? Is there any other point where you have the same potential? Yeah, all over here. So all over this region, same distance. This line is called an equipotential line. So equipotential can be a line, can be a surface. You know, if you look at it in a three-dimensional format, suppose I have a charge here, a point charge. Around the point charge you have equipotentials, right? So you can imagine a spherical surface. So the surface you can have a surface of a sphere having the same potential. So we call that equipotentials. How many equipotentials are there around this charge? Infinite number. You can have equipotentials here, here, here. You can have equipotentials anywhere. So what is an equipotential line or a surface? It is the locus of all the points having the same potentials. It's a locus of all the points. Locus means connection. It's a locus of all the points having the same potentials. Now, on a two-dimensional plane, you'll see it comes out as circles. On a three-dimensional format, you'll see a spherical surface. So, equipotential surfaces or equipotential lines are lines or surfaces formed by connecting all the points having the same potentials. And you can see that there are infinite number of them. Now, which of these potentials is higher? The closer one is higher. Obviously, the closer one is higher, and the other one is lower. Now, where are the electric field lines here? Where are the electric field lines? Electric field lines are going this way. Those are the electric field lines. Now, what do you see as a remarkable geometric feature between electric field line and equipotential line?
Perpendicular.
Perpendicular. The equipotential lines, you said it?
Yeah.
The equipotential lines are perpendicular always to the field lines. They'll always be perpendicular to the field lines, always. The equipotential surfaces or lines are always perpendicular to the field lines. So if you know how the field lines are going somewhere, you can actually figure out which way the electric potential lines are supposed, equipotential lines are supposed to be. Now this is from a point charge, but if you have a couple of charges floating around here, then the equipotential surfaces won't be spherical or circular. You can do it. It can be going in different directions. So the equipotential surfaces, pretty much like your weather on your weather map. Have you seen the pressure, equal pressure points plotted? They'll make a curve like that, and they'll make another. You can see all those lines are parallel lines. Have you seen them on a weather map? They'll draw those parallel lines. They'll all be like having a similar shape, and on one side they'll put a capital H, and on the other side they'll put a small L. Capital H will be red in color, and the L will be blue in color, just to say high pressure, low pressure. And always those lines are going to be going from high pressure to low pressure. You can check it out on the weather map. You can see that the way they are kind of curving it, the high pressure is always on the inside, going towards low pressure. So why they are pointing it out that way is because thunderstorms and clouds and all those things are going to move along with that. So high pressure area, low pressure area, obviously movement is going to be expected from high to low. Same way here. We have low potential areas here, high potential areas here. The electric field will be running from high to low, and they'll be cutting across those equipotential lines at right angles. Okay. Between parallel plates, those are parallel plates. And if these are charged positively and negatively, I already drew the electric field lines, right, between them. Where are the electric field lines? The field lines run from positive to negative. and then from here, goes like that. So the field lines are going, from positive to negative, you can see the curvature. What about the electric potential lines? Equipotential lines, yeah.
Perpendicular.
Perpendicular to that, you're going to have perpendicular lines. So you can have an equipotential line here. So if this is a 100-volt potential, and this side is a 0-volt potential. So what is the potential difference? 100 volts, right? So potential difference from here to here is 100 volts. What is the middle line? How many volts? 50. So the middle line is going to be 50 volts. So this equipotential line, the red line, equipotential lines won't have any arrows. Okay? So this red line that I've drawn here is right in between 100 and 0. So that's an equipotential of 50 volts. What if there's a line here? How many volts is that?
75.
75. Common sense, right? That's 75 because the potential gradient is exactly uniform because it's uniform electric field. Because it's uniform electric field, the drop in the potential is linear. Okay? So from 100 goes 75 to 50 to 25 to 0. So that's a 75 volt line. And this equipotential line over here is a 25 volt line. Equipotential. How is the shape of this going to be here outside? What's the shape of this going to be on the outside?
It's gonna be
Curve.
perpendicular.
It's going to be perpendicular. See the perpendicular thing here? So it's going to curve like that. So you have regions of same potentials, and that's what we call as equipotentials. So those are the equipotential lines. And if there is one here, then it's going to have a higher potential, and it's going to go like this. This blue line that you see here, which is the terminal on this side, the plate on this side, is at an equipotential of 100 volts. And this one is at 0 volts. Now, it's not necessary that you will be given always 100 and 0. You can be given different numbers. Like suppose you are given the electric plates and you're given 100 volts and negative 40 volts. What is the middle line?
30.
So the middle line, what you do is this. This is 100 and this is 40. What's the potential difference? 140. So from here to here there is a 140 drop. So from here to the middle it should be a 70 volt drop. So this is going to be dropped to 30. Okay? So what is this one? What is that equipotential line? Yeah, it's exactly between these two, or you can just go by the gradient. How much is this? Negative 5. This one? 65. So you can see the way it is dropping is very proportional. So from here to here the drop is 140. So from here to the middle it should be 70. From here to here it should be a drop of 35. Drop of 35. From 100, a drop of 35 brings you to 65. Drop of 35 to 30. Drop of 35. Drop of 35. Okay? So it is not necessary that you should have always 0 on this side and 100 on this side. You can have negative here and negative there also. You can have both sides negative. Or you can have both sides positive. So even if it is negative on both sides, still you call one side higher than the other, right? So if I give you two plates And if I say this is negative 50 volts, and this is negative 20 volts, which is a higher potential? This side is higher potential, and this side is lower potential. So which way is the electric field going to be directed? From this side to this side. So electric fields are going to be this way. Electric field always goes from high potential to low potential. If you remember that, this is high, this is low. So never think about, don't think that it's always going from positive to negative. It's always easier to think about high and low, okay? Because here, none of them are positive. But of course, this is more positive than this one. So it doesn't have to be a positively charged plate. You can have two negatively charged plates and run and have an electric field between. That's possible. So what is the electric field? It is that will be the force acting on a unit positive charge but released there. So this is negative 20, a higher potential. This is negative 50, a lower potential. So there is a potential difference. And this is high to low. So the electric field is directed that way. And potential lines are going to be this way, here in the middle. So those are the electric potential lines, the equipotential lines. Now what is this potential? This is negative 20, this is negative 50. What is this line?
30.
Negative 35. It's exactly supposed to be midway. Okay, let's continue this sentence. If I release an electron here, which way will the electron go? To the right, because it's going against the field, right? So the electron is going to rush this way. When this electron goes and hits this plate, what will be its kinetic energy? What will be the energy of that electron when it goes and hits this plate? So how do you do it? How do you work out the kinetic energy of this electron when it goes and hits there?
Half of v squared.
Yes, but I don't have velocity. Kinetic energy is half mv squared, but now I need to find out how much energy will this electron have when it goes and crashes on that plate. Yes.
Use W was QV.
QV. W is the work done or energy acquired, which is equal to QV. We work with that. And the charge of an electron is 1.6 10 power minus 19. And what's the potential difference? 30. You understand why the potential difference is 30? This is negative 50 and that's negative 20, so the difference between them is 30. Okay? So multiply this, and the answer is 4.8 times 10 to the power of. That is the energy with which this electron is going to crash onto the plate. Now, extending that question further, how fast is it hitting that plate? How fast is that electron hitting the plate? This is the energy, this is the kinetic energy. The work done is the same as the kinetic energy, because the energy acquired by the electron is in the form of kinetic, it's a motion energy. So this electron is moving from here to here, it is picking up kinetic energy and it is crashing there with an energy of this. Now my next question is, how fast is it crashing on that plate? How fast is it hitting the plate? So what do you do now? Equate this to what? 1/2 mv squared, because you know the kinetic energy formula is half mv squared. So the kinetic energy is equal to half mv squared. So you have 4.8 times 10 to the power of negative 18 is equal to half times 9.11 times 10 to the power negative 31. That is the kinetic energy, that is the mass of the electron, times v squared. Solve for v. Let me know what you get. How much is the velocity? Yes,
So 3.25 times 10 to the 6.
I don't know, but it looks like 3.25 times 10 to the power 6 meters per second. Everyone make sure that you're getting it. Just make sure that you're getting the right answer. 3.2. I don't know if it is right, but just check. So all you do is equate half mv squared to the kinetic energy that you just got, and you have it there. So you can figure out how fast the electrons are going to crash onto the screen, onto the plane. So if you know the potential difference between 2 points, you can actually figure out a lot more like this. You can find out how fast the electron is going to hit the plate. So what is pulling that electron in that direction is the potential difference. Is that the answer? Yes. So push all those things to one side, get v squared, and then take square root of that, you get the answer. Make sure you're getting that answer. Simple calculation, but if you don't get that right, then it's a problem. Use the exponents button, and that will be the best way to go. The double E. So if you're plugging this into the calculator, you'll put 2 times this is 9.6. So you type 9.6 E negative 18, then divided by 9.11 E negative 31, and then take the square root of that. That's pretty much what you should type in the calculator if you don't want to make mistakes. 9.6 E negative 18 is this part times 2, divided by this will give you v squared, and then take the square root of the answer. You should get it. Got it? Are we on the right track? Now what if there is a hole over here? Suppose there is a tiny hole over here. What will happen to that electron is it won't strike the plate, instead it will shoot out through that hole. So how fast is the electron going to get out of that hole? It's going to come out at that speed. Okay? It's going to come out at that speed. This is what we call as an electron gun. You can shoot an electron. This is called an electron gun. So what is an electron gun? You need a source of electrons. You can create electrons by just heating a wire. If you heat a wire, you can create electrons, because when you heat something, the electrons can get loosened up because they get enough energy, they escape. Okay? So they're called thermal electrons. When you heat something, like your hot plate. Suppose you have a heating coil and you heat that coil by electricity, and as soon as you see it's red hot, there are electrons sprayed out from it. There are electrons coming out from it. And those electrons are called thermions, or thermal ions, or thermal electrons. Okay. So you can heat a metal plate or a filament of a bulb, and you can produce electrons. And what happens to the electrons after that depends on what you're going to do. You create a potential difference. What will happen to that electrons? The electron starts rushing, and then it comes out from there. It comes out at high speeds, and that's what we use. Where's the electron gun used? Where's the electron gun used? Any clue? Yes. Microwave Microwave is a magnetron. It uses a magnetron. It generates electromagnetic waves. Like, I don't think there's an electron gun there.
Is it used on when you like spray that like paint or something? What kind of paint is that?
Electrostatic sort of thing.
Something like that.
Yeah, electrostatic. Yeah, to create electrostatics. But again, that one is the spray. The spray. Each droplet gets ionized. That's the only thing. And the ionized particles get attracted by the other plates. So that's a different one. But yeah, idea is the same. But pretty much exactly like what I said just now. Electron generated and then made to accelerate like this, and then the electron comes out from one side.
LTVs.
Which one?
LTVs.
The old televisions, yeah, the televisions which has got a bulb. So in the old televisions, we have electron guns, not this one. So the old televisions, they have they're not supposed to shut up. I can't help it, Mr. Wiedmar is behind saying, go louder. Okay, so this is the bulb. This is the screen that you watch the pictures on. And what's behind, over here, there's a filament. At the very end, there's a filament. And what we normally do to that filament is we give a small voltage to the filament, and so the filament glows, lights up. Not like lights up that way, but it will be like yellowish. So this one lights up, and so it starts producing thermal electrons. And then from here, those thermal electrons have to be accelerated. So we have an anode. It's a cylindrical kind of an anode. So between the anode and this point, we connect a high voltage. And this is an electron. If the electron has to be accelerated, what should be the polarity of this? I said anode, so it's positive, right? It's supposed to be positive. And then negative. Now, how many volts in the television picture tube? This potential difference could be 10,000, 20,000 volts. Why such high potential difference? Because we want to accelerate that electron really well, high speed. So when the electron comes out from here, it gets accelerated and it goes through the middle of the cylindrical anode. It's actually focused through the middle. There's a different focusing mechanism. So what it does is actually kind of makes it go through a certain region. So it comes out from here. And before it goes here, there are some grids over here. The grids are supposed to be used for brightness control. So have you changed the brightness of a television? What you're doing by changing the brightness is trying to limit the number of electrons going across. So we have brightness controls and we have other controls like that. So what happens to this electron is it goes and hits the screen. And the screen is coated with fluorescent material, zinc sulfide, generally used. So for a cathode ray tube, it's zinc sulfide, but for picture tube of televisions, they use other materials. Now, that zinc sulfide or this coating, which is a fluorescent material, what happens is, as the electron goes and strikes the fluorescent material, it gives all the kinetic energy it has to that particular region. And then it causes the fluorescence at that spot. Get it? So it makes a spot appear on the screen. Now when a spot appears on the screen, suppose we have two plates connected to a potential difference. Imagine I have a positive potential and a negative potential connected to the two plates which are horizontal with that. What will happen if I connect a potential difference positive here, negative? What will happen to this electron beam? This is positive and this is negative, and what's going through the middle is an electron. So which way will this electron go? Up. Because it's negative, right? The electrons are negatively charged, so it will go upward. So what will happen is the spot, instead of going there, will go there. Get it? What if I connect an alternating voltage here, not direct voltage? What do you mean by alternating voltage? Like the voltage that's coming here as alternating. It's plus, minus, it flips all the time. It flips 60 times per second. This one is 60 hertz, which means like the voltage is not positive on one side, negative on one side all the time. It's flipping 60 times per second. That's what we call as alternating current. So what we have at our homes, they're all AC. Okay? So if I connect AC, what will happen to the spot? It will go to the top when the cycle comes there, and the next cycle is when the bottom becomes positive. So what will happen is this electron beam that goes and hits the middle will get deflected to the top, then quickly will get deflected to the bottom, then again to the top, again to the bottom. Keep doing that. What will be seen on the screen? What will you see on the screen if this continues? You will see a line. You will see actually a line. If it is done too fast, you will see just two spots on both sides because it's stopping and turning around over there, but the middle is going too fast, so you won't see the middle line at all. But if it's if it's made to go with a steady speed, you will see the line like that. Now, what if we use another set of plates which are vertical plates like that? So you're connecting. Can you imagine what I've drawn? So the blue ones are like this, and the red ones are like this. So if I connect another set of plates, parallel plates, and if I connect a voltage here, what will happen to the beam? It will deflect. So this is how it goes. It goes to center, but when I put the top plate and bottom plate, it can go up and down. And if I put sideways plates, it can go left and right as well. So if I put both together on, it will go up and down and then go left and right. But the left and right movement is a special kind of a wave, a signal that's applied. The left and right one, this one is a special signal. The signal goes up like that, or from here, it goes up, and as soon as it reaches that side, immediately it flips back to the same old value and then goes again. So that is alternating, but is alternating in a very special style. What is a special style? The voltage actually is going from a negative value to a positive value, and all of a sudden starts over again from the negative value to the positive value. So this is a flyback. We call this signal a sawtooth signal. Sawtooth. So when we give this signal, what will happen is the spot from the left hand side will scan on the screen to the right hand side, and then all of a sudden go back to the left hand side. See? And then again scan till here, and again all of a sudden go. So you'll see the spot going to this side, quickly coming back again and going, scanning again, scan again, scan again. Now if I connect this signal to the vertical plates and the horizontal signal, the same old thing. So what you'll be seeing on the screen, you'll see this. Again. Again. You understand? So you'll see a sine wave, and all of a sudden come back again and create one more sine, and then again. And so you'll see a wave appearance on the screen. So a cathode ray oscilloscope is a device that we use to study the different kind of signals this is pretty much what is in it, in a cathode ray tube. And a cathode ray tube is the kind of tube that we use in a television also. Okay? In a television, instead of these plates, they use magnetic coils. And the signal that is coming from the television antenna is fed over there. And so it is creating lots of spots on the screen. It scans like that multiple times. And when it scans multiple times, it is creating spots of different intensities at different spots, and then it creates an image. So it's a lot more going on a screen than you can imagine. Yes?
So like, when you have a TV box, does that convert from the station's signal into a signal your TV processes?
From the station, it is sending out in the form of electromagnetic waves, and then your antenna will pick up those electromagnetic waves and then bring that signal in, and signal is connected to your deflection coils. And then once it goes through the deflection coils, then it will put the image on the screen. Let me see if it is. Well, this used to be here, and it died, and therefore we decided to kind of open it up, and so you can see the back of it. They removed all the big things. Now this is the bulb that you see there. Can you see the shape? Can you see all this? Here is where the filament is. If you kind of closely look, you'll see the filament also inside there. And when this is turned on, that will light up, and this itself is the anode. So the anode is connected. You can see the big terminal there. See? Okay, this is the terminal where the anode is connected. Now, this is something that is dangerous to play with, because, as I said, the voltage is what? 20,000 volts on the picture tube. Between the picture tube and inside here is 20,000 volts. And of course, the circuits will have that. So if someone is not aware of those things, will end up touching and getting a fatal shock. Now, can you see this thing? This is the magnetic, instead of the vertical plates and the horizontal plates, it's a coil from the outside. That's a coil. You can see the coil is what creates the picture on there. So if the picture is working, and if I just twist it like that, the whole picture will turn around. Yeah. And these things are slight magnetic. See, I didn't know this at all when I made my first television. That was a black and white television. When I made my first television, when I was, which year was it? 1987. Yeah, no, I think it was 86. Yeah, when I got my job and I was like, I have a house and all that, I said, I need a television, I need something. So my first 2 years and all that, I was busy teaching, really. And after that, I said, okay, now is the time to explore and do something. So one of my first projects is to make my own television. Instead of buying one, just make one. So I didn't spend too much money on a black and white television. I spent for the picture. I bought all these things separately. I made a wooden box. So I didn't get this material and all that. I made a wooden box, mounted the picture tube and all that stuff. So it was all like, there's no brand name. It's my name, basically. So initially I thought of keeping all those things on the wall, like spread out. The circuits are all spread out like that on the wall. But then it's not going to be easy to move around. So therefore I said, no, we'll put it into a box and keep it contained. So I bought the television, the black and why I went for black and white is because it was my project, the first time project, so I don't want to mess it up. So if I took a color television picture tube and if I messed it up, it's going to be more expensive. So I said, okay, black and white is all right. Let me see if it works. If it works, then I spend only that much. I spent $30 altogether, picture tube, and the circuit boards and all those things. Now the circuit boards, I had to assemble it. There you go. That's better. So that is the electron guns assembly. This is where the electron is created, and the electron is accelerated to the anode of the tube and the screen. So this is a deflection coil. Anyway, so when I made my first television, I saw these things on the television tube like this. I saw this and I didn't have a clue what they are. What is that for? I looked into manuals and like all the television manuals. Nothing is mentioned about that. Everything, so many things are there, but nothing specifically about this. Okay, and I was like, I really troubled myself on that because I didn't know the answer for it as to what it is. I got my television working, assembled everything, and it started working. But always that question was in my mind, what is that? What is that? What is that supposed to be? And you won't believe this, but I got to say it. I got the answer in a dream. Seriously. I got the answer in a dream. I was sleeping because, that's when I started believing that, your brain has the capacity to kind of start working on its own once you give it all the data. You feed it with all the data and it'll start working on its own. I didn't have a clue what it is, and I was totally lost on that. When I was sleeping in the middle of the night, all of a sudden an answer just popped into my head. And I got up immediately and I said, is that what it is? Let me see if it works. And at that time there was no television signal there. It's not like 24 hours. I got to wait until 6 o'clock in the morning when they put that pattern on the screen and then the news comes up and all that. So I got that idea. And then I went back to sleep. And early morning I got up, put the television on, opened it up, and what the answer of what I got was these are magnetic, and probably these are used for adjusting the picture, the borders of the picture to adjust the picture sides. And that was exactly what it was. The answer was exactly that. So when I started moving this, I could see the picture at the bottom and all that like twisting. So I put it back again in the right manner so it will be absolutely flat. Perfect. That's one time I got the answer. There was another moment when I got an answer because I was a new teacher, at that time. So sometimes students bring questions, challenging questions to me. Very challenging. The batch I was teaching, they were the smartest kids. So knowing that I'm a new teacher, they just want to trouble me. Some of them have the troubling intention, but some of them genuinely want to ask questions. So when they ask questions, I tell them, okay, I'll get you the answer later on. I don't know the answer right now. So I'll be, frank with them. I say, all right, I don't know the answer right now, but I'll find it out. And they trusted me that way. But then after that is my work. There was no Google at that time. I had to really do my work, which is go to the library and pick up something and use my head and just kind of look around for the answers. I have to solve it. It's a big problem that they gave me, and I had to work it out, and I want to get the answers. So I really troubled on a particular problem for so much time. I couldn't answer the question, and I was wondering what I'll do the next day, because I told them I'll come up with the answers, and I was like, what answers can I give the next day, and again, you won't believe, I slept over the book. I was like solving it and I was like tired. I put my hands like that and then slept on the table instead of sleeping on the bed. I slept on the table and all of a sudden again, I just woke up with the answer. I said, is that the way to do it? Just like that, just popped up with the answer. And then immediately, before even I went to my bed and slept, I said, let me try it. And I kept trying it out with that method, and then finally got the answer. I was like, So when I was really struggling, I didn't get the answer. Sleeping, he just suddenly threw the answer up. And I got that. Now, that was the second time I got that, and of course, that was the last time. You don't get answers like that all the time. But one thing I understood at that moment is this: if you feed in a lot of data and really tell your brain to, struggle with it, the brain will keep working in the background, and then it will start sorting out things. It will do its work. Even when you're not really conscious, it will start doing its work. Anyway, so this is something that I remember from that. All these things are meant for controlling the picture edges, which I didn't have a clue. Anyway, that's an electron gun. I was thinking of fixing the television first, but then that itself is more than 35 years old. And fixing it, it's useless because it may require me spending more than $50 to fix it. What's the point? Putting $50 and fixing it, and in the end you still have an old television. So I said, okay, now it's not worth it. And that's why I told the school, can I bring that television down because it's not working? Can I just open it up and try to see what's wrong? They said, no, that belongs to channel 1 or something like that, because a company installed all these things. So they are the ones who are authorized to do it. And then after that, I brought it down. Then I told them to mount this up. After this was mounted, this was lying in the lab, I just went ahead and opened it. So there's no channel 1 going to come up and ask for this old television. So I just opened it up and in fact, I used a part from there in there. Capacitor. That's what we're going to learn next. Okay, so electron gun is pretty much used in cathode ray oscilloscopes. Okay. You should be in a position to do the homework assigned. I think I've assigned it for tomorrow to you, right?
Tomorrow.
I'll push it further down. I'll make it Friday due. Okay, so it will be okay. Push that stop button.
Turn it off.
Yeah, stop button.